First of all, good afternoon for all of you. I will talk about this stuff of break group theory and the connection with the homotopy groups of the two-sphere using simplicial homotopy theory. And this is a joint work with John Waschke from France. Okay, so let me start with the first four. What is the goal, the object of this talk? So, sorry, okay, no, here. So, some notation. Let Pn M denote the pure break group with n strings over a surface n. And when we talk about the classical Artin break groups, we just write Pn instead Pn of the disk. Okay, this is some well-known convention. I will denote by Z of G, the center of a group. Okay, that is common. In this talk, I will use the notion of symmetrical mutator subgroup. This notion was introduced by Mikhailov and other collaborators, was explored also by Jinjian Li and Jivu, and in particular was used in this work of Bardakov, Mikhailov, Vershinin, and Wu, exploring some Bronium braids on surfaces. And the notion is as follows in the definition. So if we have n normal subgroups of a group G, so we take this notation, okay, that means the product of these iterated commutators subgroups, okay, varying the permutations in the symmetric group on n elements. Okay. So we will use this notion of symmetrical mutator subgroup to give the connection of these terms as follows. I will start mentioning the main result of this talk, and it's as follows. For n greater or equal than 2, and when we have a surface being the disk or the two-sphere, so we obtain these two isomorphisms. That means we take the center of this quotient where the module part is a symmetric subgroup. This notation means the classical normal closure of an element in this group, similar in the other part. Okay, the center of this quotient of break groups is isomorphic to the homotopy groups of the sphere times the center of the Artin break group. And in the second case, this Z2 pair means the center of the pure break groups over the sphere. So in some sense, it's possible to recover the homotopy groups of the sphere times Z or times Z2 as the center of this kind of quotients of break groups. Okay. So I will explain now how to obtain this isomorphism. Well, I will use some tools from classical simplicial homotopy theory. This is the classical version. It's not necessarily using category and functors or this kind of language. Yeah. But I will use the classical one from Curtis, Daniel Kahn, and J. Moore also. So the definition is, the first definition is a simplicial group. It's a sequence of groups together with phases maps, the decreasing ones, and degeneracy maps is the increasing ones, and satisfying some called simplicial identities. So we have here the identities just for phases maps, just for degeneracy maps, and also the mixed ones. So this structure is a simplicial group, and we may obtain the Moore complex of this simplicial group, just taking the all intersection of the kernels of these phases maps. Okay. We don't consider here the case A equal to 0 because this is the boundary map. The boundary map in this Moore complex it becomes a chain complex. Okay. So we may define more boundaries, more cycles in the natural way, yeah. And the Moore homotopy group is defined as the homology of this shape complex, of the Moore shape complex, okay? So the nth Moore homotopy group is just cycles, module, boundaries of this shape complex of G. Perfect. So we will use this notion of simplicial group applied to braid groups over the this and over the three. Okay, so I will state a technical, but the key point, a technical result, but this is the key point to obtain the isomorphism that I will explain here today. So we will start with a simplicial, sorry, it is not a simplicial group, it is just a collection of groups with one marked homomorphism, delta n plus one. Okay. I repeat, G is not necessarily a simplicial group because I don't have the total phase maps and the degeneracy maps. But I will take Hn, the kernel of this homomorphism, and we call it H calligraphic as the total set of this Hn. And we will suppose that it is a simplicial group. That means there exist phases maps and degeneracy maps in that way that calligraphic H is a simplicial group. Okay. So the simplicial group is not the Gn, but a collection of subgroups of Gn for each n will be a simplicial group. Okay. For technical reasons, now is some technical reasons in order to this part work well. So we will suppose that the center of this Hn-1 is trivial. This result is stated for fixed n. Of course, if the following condition holds for every n, so we will the consequence for every n. Okay. So the first condition is the following: the homomorphism delta n plus one given here for G, and the restriction for the center of the Gn plus one on Gn need to be surjected. Okay, epimorphism. The second condition is that the boundaries of this simplicial group H is a normal subgroup of Gn plus one. So I would like to take some quotient. So the natural quotient will be Gn plus one module the boundaries of the simplicial group H. Some other condition is that the center of this quotient intersecting the projection of the center of Gn plus one under the natural projection, this is the canonical one, need to be trivial. So I would like to don't have non-trivial elements for these both groups. And the last condition is a little bit more technical, maybe is some condition inspired by something so-called the central extension theory in simplicial homotopy theory. That means that I have some collection of generators of Gn plus one. Then for every element in this collection, there exists some index and a map, something like a lifting, some lift, such that the restriction to the kernel, to the Hn plus one, is equal to some one of the phase maps for this graphic H that is the simplicial group. So the other part is that we would like to have non-trivial elements in this intersection. It's really a technical part in order to construct the following isomorphism. So if I have these conditions, we may conclude that the center of Gn plus one module the boundaries of the simplicial group H is isomorphic to the homotopy group pi n of H times an plus 1, that is the projection of the center of Gn plus 1 under the canonical projection as stated in condition 3. So this is a general result, obviously, but what is the point? Of course, all these conditions are satisfied from pure braid groups, in particular for periods over the disk, but are satisfied from braids over other surfaces also. And so just to mention something, so if we would like to take here in the numerator pure braid groups, we will have in the module, we will have some kind of boundary or something. And the idea is that pi n of h will be isomorphic to the homotopy groups of the sphere. So we will explain how to apply this theorem 1 for the case of pure braid groups. So first of all, let me introduce some possible way to induce, given a collection of a sequence of groups without any structure, if we know that G is some simplicial group, it is very natural to induce a simplicial structure of the sequence of group H. It's very natural, like the diagrams are illustrating here. So if we know that there exists phases maps for Gn and there exists this isomorphism, so we may induce naturally a phase map here for Hn and degeneracy maps for Hn also. It's very easy to verify that they satisfy the simplicial identities. Okay. So given that, the idea is try to identify some classical simplicial groups that are related to the homotopy groups of the sphere, and then identify these classical simplicial groups with some subgroups, sequences of subgroups of the pure braids over surfaces. So we will start in this way. Given a collection of endpoints inside of the disk, we will consider these generators. These generators are very appropriate because we want to get these generators in pure braid groups over the disk in a few minutes. So we take these generators. We have this K calligraphic given by the fundamental groups of this pure disk. Okay, we know that these groups are free groups, and we define the following maps. It's very natural to define these following maps when we know some basic facts about simplicial groups given by free groups, in particular the Milnor free group construction of the sphere S1. So we define these maps. These maps are in fact simplicial maps. They satisfy the simplicial identities. So K turns to be isomorphic as a simplicial group, in fact, to the Milnor free group construction of the simplicial sphere S1. In some way, we have this collection of free groups, and we define the phases and the degeneracies in the same way as we as well defined for the Milnor free group construction of the simplicial sphere S1. Hence, given it follows from a theory of Milnor that the geometric realization of K is homotopy equivalent to the loop space of the S2. So naturally, we have this isomorphism. Pn of K is isomorphic to pi n of the Milnor free group construction of the sphere S1. And since it is homotopy, the geometric realization is homotopy equivalent to the loop space, so we have this last isomorphism. Be careful with some notation. This part is a homotopy group in the simplicial homotopy theory. This part is a homotopy group in simplicial homotopy theory, and this is the well-known homotopy group of the sphere. Yeah, it's the same notation, but of course they means in some moment different stuff. Okay. Well, so we have this K. This is this key. This K is a simplicity group, very important for the development here in order to give the connection with pure braids over surface. So now we recall some information about the pure braid groups over a surface. So it is defined, the pure braid group over a surface N with N strings is defined as the fundamental group of this ordered configuration space. Okay, the notation is Pn of M, and when we have the disk, the classical Artin braid groups, so we just write Pn instead of Pn of D2. And there are natural forgetting maps when you forget one string. And these forgetting maps are the I, okay, when we are forgetting the I string. And geometrically, it's just forgetting one string. And from the point of view of the configuration spaces, we are forgetting one coordinate. Okay. This is just it. And we may define some two subgroups of the pure braid groups over surfaces. The first one is the called Bronium braid group. This Bronium braid group of N strings over N is the intersection of the kernel of all the forgetting maps. I highlight here with red the I equal to 1 and the almost Bronium braid start with A equal to, okay? It's not the complete intersection of kernel, but almost the complete intersection of kernels, okay? It is very well known that these Bronium braids were used from Berry, Cohen, Wong, and Wu to establish the first connection of braids over surfaces and the homotopy groups of the sphere using Bronium braids. Okay. Let me show some examples how it looks like these braids. So here we have an example of an almost Bronium braid over the disk. So I keep the first one, just the first string, just vertical. And I'm illustrating here what happened if we forget this third string. So we forget this third string, and we have this free braid, and we start to move the strings in a very natural way, obtaining the trivial braid with 3 strings. And so it is more or less similar. If we forget the second or the fourth string, we obtain also the trivial braid, but not when we remove the first one. This braid given by these 3 strings, the last 3, is not a trivial braid. So this is an example of an almost Bronium braid over the disk, and this is an example of a Bronium braid over the sphere. In some sense, it's just the same braid like the first one. The point is when we remove the second, the third, or the fourth string, we have the movement in some tubular neighborhoods, is some part of the disk. We have the trivial braid, and we forget the first string. Now it's possible to do some movement, allow it in braids over the sphere. So in fact, this seems like a dish, but in fact, these are 2 spheres, and we may go around this sphere and do the movements in order to complete the movement and give and we get the trivial braid. So it is an example of a Bronium braid with 4 strings over the sphere. Well, we will use these Bronium and almost Bronium braids in this talk to establish the isomorphism that we desire. We will use also some geometric generators. So the IAJ that I talked when I started to establish the main result. These AIJ are these elements, are the natural geometric generators of purebred groups over the disk. This is the classical one from Artin. And when we have the inclusion of the disk on the sphere, we just take this element as generators for the purebred group over the sphere also. So AIJ will mean a purebred group over the disk or over the sphere, and in fact, the total collection will be a set of generators for these purebred groups. Okay. Well, there is a well-known Fadelnevert fibration of configuration spaces that give this short exact sequence is taken as fundamental groups of the corresponding configuration spaces. And the good point in this part is that the kernel of Dn+1 is this free group. And if we will recall the group K, let me just recall quickly. I was interested in this kind of groups by one of the Punter disk, okay? And we say that the collection K given by this total collection of free groups is a simplicial group and is isomorphic as simplicial group to the Milnor free group construction of the simplest sphere S1. And so we know that Pn of K is isomorphic to Pn+1 of the sphere. So it's very important, this collection K, and it will appear as the kernel here, as the kernel of the last forgetting map. Okay. This is natural to give the inclusion here, just taking the generator Yj given to A, J+1, N+1. This is very natural. It's just something like you have the projection over the disk and you just take this, this loop times 0, 1, just giving it, and you have the natural inclusion of the fundamental group of the Punter disk inside the purebred group over the disk. Okay. Well, so we have these forgetting maps, a total collection of forgetting maps. Then we create this KD2 as the kernel of these forgetting maps. But recall that the kernel of these forgetting maps are just the fundamental groups of the Punter disk. That means something like the group K. Okay. So we induce using the group, the simplicial group K, we induce using lemma 1 a simplicial structure on the group KD2. Okay. So it is very natural inducing this simplicial structure. This is very natural to have that Pn of K of D2 is isomorphic to Pn+1 of the sphere S2, as established here in this proposition. Well, we are almost collecting some basic facts in order to prove the isomorphism that we want to prove. Okay. Now, let me talk a little bit about braid groups over the sphere. Just, it's very similar. It's a very similar procedure to the last one about the disk. Well, we also have a Fadelnevert fibration, but in this time it works for n greater or equal than 2. We collect the kernels of this homomorphism, forgetting maps, and we complete in the first steps. We need to complete for some technical reason. Yeah, it's just to give the complete collection of free groups of every rank that we deserve. And okay, in this case, we see the fundamental group of the Punter sphere as a free group, but adding one more generator and having this relation. But it's just technical in order to give some isomorphism that I will explain in a few minutes. Okay, taking in this way A of S2, like the kernels of these maps, and completing the lower cases in this way, it's possible to prove that that collection of groups is isomorphic in every level, is isomorphic to these free groups of ranking given by in a paper of Berry-Cohen von Anvu. Is just as I say, adding one generator and taking the total product of elements as a relation. And the important point is that this group F hat is isomorphic as a simplicial group to the Milnor free group construction of the sphere S1. And we have this isomorphism described in blue. So this is very natural to have this second proposition using the simplicial group F hat. We induce a simplicial structure on the sequence of groups K of S2. Of course, because F hat is isomorphic as simplicial group to the Milnor free group construction of the simplicial sphere S1, so we obtain this isomorphism of P and K of S2 with Pn plus 1 of S2. Again, I remark that the left-hand side is a simplicial homotopy group, and in the right-hand side is the geometric natural homotopy group. Okay. Well, so the idea now is apply the technical theorem 1 in these two cases. The first case is for the arcing braid groups, the pure braid groups over the disk. And the second case is the pure braid groups over the sphere. So if we want to apply theorem 1, we need to check some information as the following. Well, we need to take this collection of groups with one marked homomorphism, delta n plus 1 in each level. We set Hn to be the kernel, but in this case it's very nice because the kernel is a free group, is related with this Milnor free group construction of the sphere S1. So this calligraphic H will be natural a simplicial group. And from the final negative fibration, we know that the groups Hn minus 1 are free groups. So the center is trivial. Okay? I apologize here. In fact, it's the center of the kernel of delta n. Okay? And it is trivial, of course, the center of the group is trivial. And also we need to verify some conditions, these 4 conditions. So the homomorphism delta n plus 1, where delta n plus 1, recall, is the forgetting map dn plus 1 for the disk, and delta n plus 1 is the forgetting map dn plus 2. I need some shift here for the sphere. And so we need to verify that the homomorphism delta n plus 1 and the restriction to the center are surjectives. But this is very natural because they are just projections, the forgetting maps. The second one is that the boundaries give a normal subgroup of Gn plus 1. We need to verify it. The third condition is this intersection needs to be trivial. We will check a little bit more. We will check that without center, the intersection in fact is trivial. So when you have the subgroup center, naturally it will be trivial. The last condition will be verified easily because we have the total collection of forgetting maps for pure braid groups over surfaces. So we will check it. And when we will, if we verify these 4 conditions, so we will check that for this GM, when GM plus 1 is the pure Breit group over the disk, or GM plus 1 is the pure Breit group over the sphere, so we conclude this isomorphism violet, yeah, where pi n of H calligraphic will be or pi n of K of D2, or will be pi n of K of S2, and both of them are isomorph to the homotopic groups of the sphere. So we complete the result. So let me show how we verify these conditions. So first of all, this KD2N are the kernel of these forgetting maps. This sequence has a structure of simplicial group. Yep. And we have this isomorphism blue that will be very important for this part. So dn plus 1 is the first condition. Dn plus 1 is just the forgetting map. And it's part of a short exact sequence. It's natural surjective. And the center of the classical Artin Breit groups are Z. So, in fact, they are generated by the full twist. The full twist is the braid that have a complete twist of the points. The half twist is called a Garside element, and the full twist is just a complete twist of the points that are based for the braids. In fact, when we project, we forget the last string. A full twist goes to the full twist. So this dn plus 1 is in fact an isomorphism. And of course, the full twist doesn't belong to the kernel of dn plus 1. This is really important for the third condition. Okay. The second condition is about the normality of the boundaries in the total group. It follows because the boundaries of K of D2 is a symmetric commutator subgroup. And given a symmetric commutator subgroup, it will be normal in the whole group. But we have some other information. In fact, the more complexes is given by Bronium braids from a theorem of Bardakov-Mikhailov over Chinian Vu, as cited here. We have a description of this Bronium braid group as a symmetric commutator subgroup. Then, when we apply the D0 map on this more complex, we obtain these boundaries here in the second item. Okay, so we have that the boundaries are in fact normal in the whole group, and the cycles of this KD2, the simplicial group, is just this intersection. And in fact, is part of other work, but the homotopy group of this KD2 that we know that is isomorphic to the homotopy groups of the sphere. So we may conclude that this group, the kernel of D0 intersection with Bronium braid groups, module this symmetric commutator given by the boundaries is isomorphic to the homotopy groups of the sphere. It's more or less something like the first results of Berwick, Cohen, Wong, and Vu about this connection of Bronium braids and homotopy groups of the sphere. Well, the third condition means about some intersection. So we don't take the center here, it's not necessary, since the full twist doesn't belong to the kernel of the n plus 1, so and the a n plus 1 is the projection of the center over this group. So we easily conclude that this intersection is triggered. And the last condition is very easy. There exists a map. There exists an index for every index we may obtain a non-trivial element in this intersection that is part of the last technical condition in theorem 1. So we are able to verify, we are we are able to verify the conditions given in theorem 1 for the first case of the case of the disk. And we may conclude the statement in violet. I will establish in the notation that I state at the first slides in this talk. So let me now explain how it works for the simplicial group KS2 about the pure braid groups over the sphere. So we have this collection KS2N. KS2 has a structural simplicial group, is something similar. We have these isomorphisms. So verify the properties for P for KS2 is more or less the same. Okay, we have these forgetting maps that geometrically forgets the last string. The center is Z2, is generated by the full twist, also the full twist, but in this case is the full twist in the pure braid groups over the sphere. And now is a finite ordered element of order 2. But anyhow, the center is Z2, and the projection, when we forget one string, the projection of the full twist is again a full twist. And then we have that this dn plus 2 is an isomorphism, so is not just surjective, but is bijective. There is restriction to the center, so it's surjective. The total dn plus 2 is surjective. And again, we have that the full twist doesn't belong to this kernel, and also we will use this information in the precondition. Well, more or less similar. We have here the description of the more complex boundaries and cycles. I will to note here that this description of the boundaries as symmetrical mutator subgroup was not given in the article from Bardakov, Mikhailov, Bershini, and Vu. So we obtained this description in our paper. And we have this kind of information. It's more or less the same. It's, from the technical point of view, is more or less the same as we saw for the case of the disk. So let me establish the main result again. So applying theorem 1 to the braid groups over the disk and to the braid groups over the sphere, using these simplicial groups, K of D2 for the disk or K of S2 for the sphere. So using the notation of the elements as I stated before. So the boundaries are these iterated symmetric symmetrical mutator subgroups. They are iterated products of iterated commutators. And so the center of these groups are isomorphic to the homotopy groups of the sphere pi n plus 1 of S2 times the center of the pure braid group that we consider in each case. Okay. Well, just a few final comments. This work, in fact, started from a motivation from this classical paper from Berry, Cohen, Wong, and Vu. They established the connection of Bronium braids and homotopy groups of the sphere. And also from a paper from Li and Vu from 2009. So they studied the Artin braid groups and homotopy groups, and they established these isomorphisms of the center of this quotient, but they use another idea and they prove these isomorphisms the other way. So we reprove here using a different technique. For the case of the sphere, it's in fact new. And also using these ideas, we may obtain this kind of isomorphisms for other surfaces, for other pure braid groups over other surfaces. Well, this is part of of the work that I want to share with you. I hope you enjoy this kind of beautiful connection. It's very interesting, this connection of two different theories, braid groups and homotopy groups of the sphere, using simplicial homotopy theory. So that's it. Thank you so much.
Thank you. Auditorium, what about remotely?
I want to ask a question. Hello.
Yeah.
Hi. Hi. I was gonna ask, like, this is a fascinating connection. I really like it. Were you able to, like, even for the known examples of calculations of pi n plus 1 of S2, were you able to see these generators and relation and get some calculations out of this relation? Or connections between those two? Like, is there a correspondence like that you can build out of these? How far do you know?
Well, yeah, that's a good question. So at first glance, the connections for the both groups are very difficult, are very hard to train. The idea is try to explore some techniques of braid groups and try to give some information of the homotopy groups of the tree. But unhappily, until now, we don't have further development in this way. So it's not a natural question, but
I see.
yeah.
I would assume that for n equal to, even for n equal to 1, to see the explicit connection is going to be interesting. Like, we are looking at pi 3 of S2, you know, like,
Yeah,
so that
not exactly with these isomorphisms, but from the classical one, for example, from Berko and Gungavu, we establish it in another way also. It's possible to see that the close of this braid, let me show the classical one that I show for you here. Just 1 minute. Let me see. This is my examples here. Okay, right. So these three strings, don't consider the first one, okay? The second, third, and fourth strings, they are a braid, a Bronium braid, in fact, and the close of this braid is the Bronium rings. Okay?
Yeah.
And it's known that this braid projects to the eta2, the generator of pi 3 of S2.
Okay, I see.
Okay. So it's possible to recognize some kind of grades in very lower cases. It's more or less easy to recognize which kind of elements are projected, but not further development if we have.
Okay, thank you.